Right now, as you sit there watching this video, you feel completely confident about one thing. You know which way is up. You know which way is down. Your feet are on the ground. The sky is above you. Gravity is pulling you toward the earth. Everything makes sense, but what if I told you that this feeling, this absolute certainty you have about direction, is one of the greatest illusions your brain has ever created? What if I told you that in the actual universe, the real universe beyond this thin shell of atmosphere we live in, there is no up, there is no down, there is no left, no right, no top, no bottom. And this is not some abstract philosophical idea. This is hard, measurable, testable physics, and when you truly understand what this means, it will break apart everything you think you know about reality itself. Let me start with a story. A real story. A story from NASA's archives that most people have never heard. In 1998, the Space Shuttle Columbia launched on mission 90, carrying with it a laboratory called Neuralab. This was not a typical space mission. This mission was specifically designed to study what happens to the human brain when you remove gravity from the equation. And what they found terrified them. Within 72 hours of reaching orbit, astronauts began experiencing something called the visual reorientation illusion. Their brains could no longer determine which way was up. But it was worse than that. Some astronauts reported that suddenly, without warning, their entire perception of the room would flip. The ceiling would become the floor. The walls would rotate. One astronaut described the sensation of suddenly feeling like he was hanging upside down from the floor, even though there was no force pulling him in any direction. His brain was desperately trying to create a sense of direction, and it was failing catastrophically. The researchers on the ground were stunned. They had expected some disorientation. They had not expected the brain to essentially malfunction in this way. They had not expected the fundamental architecture of human perception to collapse within 3 days. And here is the thing that should send a shiver down your spine. Those astronauts were only in low Earth orbit. They were only 200 miles above your head, and their brains could not handle the absence of direction. Now imagine going to Mars. Imagine going to Jupiter. Imagine travelling between stars for years in zero gravity. What happens to the human mind when direction ceases to exist permanently? But this video is not just about astronauts getting dizzy. No, this goes so much deeper than that. Today we are going to journey from the inside of your inner ear to the equations of Einstein, to the bizarre realm of quantum mechanics, to the large-scale structure of the entire observable universe. And at every single level, at every single scale, we are going to find the same terrifying truth. Direction is not real. Up does not exist. And the implications of this single fact reach into every corner of physics, every corner of philosophy, and every corner of what it means to be a conscious being in this universe. We are going to explore how your brain manufactures the illusion of direction. We are going to see how Einstein proved that space itself has no preferred orientation. We are going to dive into quantum mechanics where particles do not even have a definite position, let alone a direction. We are going to look at the entire cosmos and ask whether the universe itself has a top or a bottom. And we are going to confront a question that will keep you awake tonight. If your brain is lying to you about something as basic as which way is up, what else is it lying to you about? If this kind of deep, mind-bending exploration of reality excites you, if you want to understand the universe at its most fundamental level, then you are in the right place. Hit that subscribe button right now, because we go this deep in every single video. Drop a comment below telling me this. Before watching this video, did you ever question whether up and down were real? I want to know your answer. And like this video because the algorithm needs to know that people want real science, deep science, not surface level explanations, but the actual truth about how reality works. Now let us begin. Let us start where all of this starts. Inside your head. Right now, deep inside each of your ears, there is a tiny organ that you have probably never thought about. It is called the vestibular system, and it is the reason you think up exists. This system has two main components. The first is 3 semicircular canals, tiny loops filled with fluid. When you rotate your head in any direction, the fluid in these canals sloshes around, and tiny hair cells detect that motion and tell your brain which way you are turning. But the rotation detection is not what we care about today. What we care about is the second component. 2 tiny organs called the utricle and the saccule. Inside these organs, there are crystals, actual crystals. They are made of calcium carbonate, and they are called otoliths. These crystals sit on top of a bed of hair cells, and gravity pulls them down. That downward pull on those crystals is literally the only reason you know which way is down right now. Think about that. Your entire sense of direction, your entire feeling of groundedness, your entire confidence about the orientation of the world around you comes from tiny rocks in your ears being pulled by gravity. That is it. That is the only signal your brain has about which way is down. Everything else, everything about how you perceive the room around you, which way the walls are oriented, which way the ceiling is, all of that is constructed by your brain based on visual cues and memory. But the fundamental anchor, the thing that tells your brain which direction to assign as down, is nothing more than rocks falling inside your skull. Now here is where this gets fascinating. In 1963, a researcher named Ashton Graybiel at the Naval Aerospace Medical Institute conducted a series of experiments that revealed something profound about how dependent we are on this system. He placed subjects in a completely dark room, strapped into a chair that could tilt in any direction. Without visual cues, he asked them to determine when they were tilted, and the results were shocking. Without vision, humans could only detect tilt angles greater than about 2 degrees using their vestibular system alone. But more importantly, when he then added a tilted visual frame, a simple tilted rectangle of light in the dark room, subjects would completely override their vestibular input and align their sense of up with the visual frame. Their eyes were overruling their gravity sensors. Their brain was choosing the visual illusion of direction over the actual physical pull of gravity on those crystals. This tells us something profound. Even here on Earth, even with gravity constantly pulling those otoliths down, your sense of up is not purely physical. It is a construction. It is a negotiation between multiple sensory inputs. And your brain will happily lie to you about which way is up if the visual information is compelling enough. You are already living in an illusion of direction. You just do not know it yet. Now let us go back to space. When an astronaut reaches orbit and enters microgravity, those otolith crystals stop being pulled in any direction. They float. The hair cells beneath them stop receiving any signal about which way is down. And this is when the brain enters crisis mode. You see, your brain was never designed to operate without a gravity signal. In all of evolutionary history, in hundreds of millions of years of evolution going back to the first fish that developed vestibular systems, there has always been a down. Always, every organism that has ever lived on this planet has had gravity telling it which way is down. Your brain literally does not have a protocol for the absence of this information. So what does it do? It panics. First, it triggers nausea. About 60 to 80% of all astronauts experience space adaptation syndrome, which is essentially severe motion sickness. But it is not caused by motion. It is caused by the absence of gravitational reference. Your brain is getting visual information that says you're in a room with walls and a ceiling and a floor. But your vestibular system is saying there is no down. These signals conflict. And your brain interprets conflicting spatial signals as poisoning. Seriously, the leading theory is that your brain has evolved to associate sensory conflict with having ingested a neurotoxin because many poisons in nature affect the vestibular system. So your brain's response to the absence of gravity is to try to make you vomit, because it thinks you have been poisoned. But the nausea is just the beginning. Over the next 48 to 72 hours, something remarkable happens. Your brain rewires itself. Neuroplasticity kicks in, and your brain begins to abandon the vestibular signal entirely. It stops waiting for gravity to tell it which way is down. Instead, it switches to a purely visual reference frame. Wherever your feet are pointing becomes down. If you flip upside down relative to another astronaut, you both feel right side up, because each of your brains is using your own body as the reference frame rather than an external gravitational pull. NASA neuroscientist Charles Oman, who spent decades studying this phenomenon at MIT, documented that this switch is not smooth. During the transition period, astronauts experience those visual reorientation illusions I mentioned earlier. Their brain is rapidly testing different hypotheses about which way is up, and it keeps getting it wrong. One astronaut on the International Space Station described looking at a module from one direction and feeling perfectly normal, then turning 90 degrees and suddenly feeling like the entire room had rotated, and he was now on the wall. His brain was desperately trying to assign a direction to a place that had none. And here is the part that really gets me. When astronauts return to Earth after weeks or months in space, their brains have to rewire again. And this readaptation can be even more disorienting than the initial adjustment to space. Astronauts returning from long-duration missions on the ISS report that for days after landing, they have to consciously think about which way is down. They drop objects expecting them to float. They feel like the floor is unstable, like it might flip on them at any moment. Their brain has learned to live without direction, and now it has to learn to trust gravity again. Studies published in the journal Neuroscience in 2016, using MRI scans of astronauts before and after spaceflight, showed actual physical changes in brain structure. The grey matter in regions responsible for spatial processing had measurably changed. The ventricles in the brain had expanded due to fluid redistribution in microgravity, and this was putting pressure on the very brain structures responsible for orientation. The astronauts' brains were being physically reshaped by the absence of up and down. So that is what happens to a human brain when direction goes away. But now I want you to think about something deeper. The brain is simply an organ that evolved to process information about the physical world. If direction does not exist in space, if it only exists where there is a gravitational field, then what is direction really? Is it a property of the universe? Or is it only a property of matter interacting with curved space-time? This question is going to take us into the most fundamental physics ever conceived, and the answer is going to disturb you. Let us go back in time. Back to 1687. Isaac Newton publishes his Principia Mathematica. In this work, Newton describes what he calls absolute space. In Newton's universe, space is like a giant invisible box. It has a fixed structure. It has directions built into it. Up, down, left, right, these are real properties of space itself. Gravity, in Newton's view, is a force that pulls objects toward other objects. When you drop a ball, it falls down because Earth's gravity is pulling it down. Down is a real direction in absolute space. For over 200 years, this was the accepted view. Direction was real. Gravity was a force that acted along a real direction in real space. Up and down existed as fundamental features of the universe, just like length and width and height, and this view made intuitive sense. Of course, up is real. You can feel it. You can see it. Objects fall down. The sky is up. What could possibly be more obvious? But then came Albert Einstein, and everything changed. In 1915, Einstein published his general theory of relativity, and in doing so he did not just modify Newton's ideas about gravity, he completely destroyed them. He destroyed the concept of absolute space. He destroyed the concept of gravity as a force. And, as we are about to see, He destroyed the concept of direction itself. Here is what Einstein realized. He called it the happiest thought of his life. Imagine you are in an elevator. The cable snaps. You are in free fall. In that moment of free fall, you are weightless. You float. Objects you release float next to you. For all you can tell, you could be in deep space, far from any planet or star, in zero gravity. You cannot distinguish between falling in a gravitational field and floating in empty space. This is the equivalence principle, and it is the foundation of everything that comes next. Now think about what this means for direction. If you are in that falling elevator, which way is down? You cannot tell. There is no experiment you can perform inside that elevator that will tell you which direction Earth is. For you, in your reference frame, there is no down. And Einstein's genius was to realize that this is not just a limitation of your senses. This is physics. This is reality. In a freely falling reference frame, gravity does not exist. And if gravity does not exist in that frame, then down does not exist in that frame. But wait, you say. Obviously down exists. The elevator is falling toward the Earth. The Earth is down there. But Einstein says no. He says what is actually happening is something far more strange. The elevator is not being pulled toward the Earth by a force. Instead, the fabric of space-time itself is curved by the mass of the Earth, and the elevator is simply following the straightest possible path through that curved space-time. That straightest possible path is called a geodesic. And here is the key insight. In the elevator's own reference frame, it is not moving down. It is not moving in any direction. It is simply existing on a geodesic in curved space-time. So what about you, sitting in your chair right now? You feel gravity. You feel a force pulling you down. Surely that means down is real for you? But Einstein says something incredible about your situation. He says you are not being pulled down by gravity. You are being pushed up by the floor. The chair you are sitting on, the ground beneath the building you are in, the entire solid structure of the Earth beneath you, all of that is pushing you upward, accelerating you upward, away from the geodesic path you would naturally follow through curved space-time. If the floor disappeared, you would follow your natural path, your geodesic, and you would be in free fall, and you would feel no direction at all. In Einstein's universe, what you experience as gravity pulling you down is actually the floor pushing you up. You are being accelerated upward constantly. Down is not a direction you are being pulled in. Down is simply the direction from which the ground is pushing against you. The feeling of weight, the feeling of down, is nothing more than the feeling of being prevented from following your natural path through curved space. This is a complete inversion of how you think about direction. In Newton's universe, you are at rest and gravity is pulling you down. In Einstein's universe, you are being accelerated upward, and what you call down is just the direction space-time is curved toward. There is no force of gravity pulling you anywhere. There is only the curvature of space-time, and your own acceleration away from natural geodesic motion. Now let us take this further. What about direction in the larger universe? In Newton's absolute space, you could in principle define an absolute up direction for the whole universe. But in Einstein's general relativity, there is no absolute space. Space is not a fixed background with built-in directions. Space is dynamic. It curves, it stretches, it warps, it twists. It is shaped by the matter and energy within it, and its shape determines what paths objects follow. But there is no universal reference frame. There is no cosmic up. Every point in the universe has its own local geometry, its own curvature. What counts as up near Earth is determined by Earth's mass curving space-time around it. What counts as up near a black hole is determined by that black hole's extreme warping of space-time. What counts as up in intergalactic space, far from any massive object? Nothing. There is no curvature. There is no preferred direction. Up simply does not exist there. And this is not just theoretical. This has been measured. The Gravity Probe B experiment, launched in 2004, directly measured the curvature of space-time around Earth using ultra-precise gyroscopes. These gyroscopes were so sensitive they could detect the frame dragging effect, where Earth's rotation actually drags the fabric of space-time around with it, twisting the very directions of space as it rotates. Think about what that means. The directions of space near Earth are not fixed. They are being rotated by Earth's spin. The direction a gyroscope points changes over time, not because of any force, but because space itself is being twisted. Direction, even near a planet, is not stable. It is being stirred like honey. Let me make this even more concrete. Imagine two astronauts, Alice and Bob. Alice is near a massive star. Bob is in empty space, far from anything. Alice defines up as the direction away from the star's centre. That makes intuitive sense. But Bob has no star. He has no reference. He cannot define up. Now Alice sends a radio signal to Bob saying, "Up is this direction." But here is the thing. As that signal travels through curved space-time, its direction changes. The signal follows a geodesic through curved space, and as it enters regions of different curvature, its direction rotates. By the time it reaches Bob, the direction Alice called up has been twisted and turned by the geometry of space itself. Bob receives the signal and has no way to align it with any local direction, because he has no local reference. This is not just a communication problem. This is physics telling us that direction is local. It only exists relative to local curvature. It cannot be transmitted across space, because the curvature of space itself changes the direction as it travels. There is no cosmic compass. There is no universal up. And this brings us to something called the connection in differential geometry, which is the mathematical tool Einstein used to describe how directions change as you move through curved space. In flat space, if you take a vector pointing up and slide it across the room, it still points up. Direction is preserved in flat space, but in curved space, if you take a vector and move it along a path, it rotates. It changes direction simply by being transported through curved geometry. This is called parallel transport, and it demonstrates that direction is path dependent in curved spacetime. The direction you arrive at depends on which path you took through space. There is no unique way to compare directions at different points in a curved spacetime. This mathematical fact has a stunning physical consequence. If you flew a spaceship in a giant loop through the curved spacetime of our solar system, starting with your nose pointed in some direction, when you return to your starting point, your nose might be pointed in a slightly different direction. Not because any force rotated you, but because direction itself is not preserved around a loop in curved space. The space you travelled through literally rotated your sense of direction. This has been measured with gyroscopes. It is real. So Einstein tells us that direction is not a feature of the universe. It is a local phenomenon, created by the curvature of space-time, different at every point, unstable, path-dependent, and non-existent in the absence of curvature. Newton's absolute up is gone. It never existed. But we are not done. Not even close. Because quantum mechanics is about to make this even stranger. Let us enter the quantum realm. And let me warn you, this is where things get truly bizarre. In the classical world of Newton and even Einstein, at least you could talk about the position of an object, the direction of its motion. An asteroid moves in a direction, a planet orbits in a plane. These things have definite orientations in space, but in quantum mechanics even this breaks down. The first thing we need to talk about is quantum spin. You have probably heard that electrons have spin. They are often described as spinning like little tops, with their spin axis pointing in some direction up or down. But this is deeply misleading. Electron spin is not rotation. The electron is not actually spinning. There is no axis. There is no physical rotation. Spin is a purely quantum mechanical property that has no analogue in the everyday world. It is called spin only because it shares certain mathematical properties with angular momentum. But the electron is not a little ball rotating in some direction. So what direction does an electron spin point? This is where reality starts to dissolve. Before you measure it, the electron's spin does not point in any direction. It is in a superposition of pointing up and pointing down, and left and right, and every other direction simultaneously. It has no orientation. Direction for a quantum particle does not exist until the moment of measurement, and when you do measure it, you have to choose a direction to measure along. You point your detector in some direction, say the vertical axis, and then and only then does the electron snap into having a spin in that direction, either up or down. But the direction it snaps into is the direction you chose to ask about. If you had pointed your detector horizontally instead, the electron would have had horizontal spin values instead. Think about what this means. The direction of a quantum property is not intrinsic to the particle. It is created by the measurement. The particle does not have a direction until you impose one on it by asking. Direction at the quantum level is not discovered. It is manufactured by the act of observation. This is not philosophy. This is experimentally verified physics. Bell test experiments, which have been performed hundreds of times with increasing precision since the 1980s, confirm that quantum particles do not have pre-existing values for directional properties before measurement. The direction truly does not exist until it is measured. The 2022 Nobel Prize in Physics was awarded to Elaine Aspect, John Clauser, and Anton Zeilinger precisely for experiments that proved this beyond any reasonable doubt. Now let us go even deeper into quantum mechanics. Let us talk about quantum reference frames. This is a relatively new area of research that is absolutely mind-bending. In 2019, a team led by physicist Kaslav Bruckner at the University of Vienna published a groundbreaking paper on quantum reference frames. Their work showed that in quantum mechanics, even the reference frame itself, the thing you use to define directions, can be in superposition. Here is what this means in simple terms. In classical physics, we always assume there is some fixed background reference frame against which we can define directions. Even in Einstein's relativity, while there is no absolute frame, we always work within some definite reference frame at a time. But Bruckner's group showed that quantum mechanics allows reference frames themselves to be in indefinite states. The very thing that defines what up means can be in a superposition of different orientations, which means that at the quantum level, the concept of direction can be fundamentally indefinite, not just unknown, not just uncertain, but genuinely not definite. Imagine that the thing you use to define up, say a gyroscope, is itself in a quantum superposition of pointing in multiple directions simultaneously. Then up itself is in superposition. Up becomes a quantum variable that does not have a single definite value. This is the reality that quantum physics describes at the most fundamental level. Direction is not just relative, as Einstein showed. It is quantumly indefinite. It may not have a single value at all. And this connects to one of the deepest mysteries in all of physics: the measurement problem. When you measure a quantum system, it seems to snap from a superposition into a definite state. But what causes this snap? What determines which direction the electron's spin ends up pointing? We do not know. After almost 100 years of quantum mechanics, we still do not have a satisfying answer. Some physicists believe all possible outcomes happen in branching parallel universes. Others believe consciousness plays a role. Others believe the math is all there is and there is nothing more to explain. But the point for our discussion is this: direction in quantum mechanics seems to require something, whether measurement, consciousness, decoherence, or branching universes, to bring it into definite existence. It is not simply there, waiting to be discovered. It is, in some deep sense, created. Now I want to take you to something that will connect quantum mechanics and direction in a truly stunning way. It is called CP symmetry. CPT stands for charge, parity and time. This is one of the most fundamental symmetries in all of physics. It states that if you take any physical process, flip all the charges, reverse all the spatial directions, which is what parity means, and reverse the flow of time, you get a physically valid process. Every single physics experiment ever conducted has confirmed CPT symmetry. But look at the middle letter. P, parity. This is about direction. Parity reversal means flipping left and right, turning the universe into its mirror image. CPT symmetry tells us that spatial direction is fundamentally connected to the flow of time and the charge of particles. You cannot separate them. If you flip direction, you must also flip time and charge to get valid physics. Direction is not an independent feature of reality. It is entangled with the most fundamental properties of the universe, time and charge. And here is where this gets really deep. In 1957, Chen Xiongwu performed an experiment that shocked the physics world. She showed that parity is violated in the weak nuclear force. Specifically, she showed that in beta decay. The electrons emitted prefer to come out in a particular direction relative to the spin of the nucleus. The weak force knows the difference between left and right. It violates mirror symmetry. This was so shocking that it won a Nobel Prize, because it meant that the universe, at a fundamental level, is not symmetric in direction. The weak force has a built-in preference for one-handedness over another. The universe, at the level of particle physics, is not direction blind. It has a subtle chirality, a handedness built into its most fundamental interactions. But wait, didn't I just spend all this time saying direction does not exist? How can the universe have a preferred handedness if direction is not real? This is one of the deepest puzzles in physics. The resolution is subtle and beautiful. The universe does not have a preferred direction in the sense of up or down. It does not have a preferred orientation in space. What it has is a preferred handedness, which is a topological property, not a geometric one. Handedness is about the relationship between different directions, not about any single direction itself. You can define left and right relative to each other and relative to the weak force's preference, but you cannot define an absolute up or down. The chirality of the weak force tells us about the internal structure of physical law, not about the orientation of space. This distinction is crucial. Direction as orientation, meaning which way is up, does not exist as a fundamental feature of reality. But direction as handedness, meaning the difference between a process and its mirror image, does appear to be fundamental. The universe does not know which way is up, but it does know the difference between left and right at the particle physics level. This is subtle, strange, and beautiful. Now let us zoom out. Way out. Let us leave the quantum world and look at the largest scales we can observe. Let us look at the entire universe and ask whether it has any preferred directions at all. In modern cosmology, one of the foundational assumptions is called the cosmological principle. This principle states that on large enough scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same at every point. Isotropic means it looks the same in every direction. If the cosmological principle is true, then the universe has absolutely no preferred directions on large scales. There is no up, no down, no special direction that is different from any other. The universe is, on average, completely symmetric in all directions, and the evidence for this is strong. The cosmic microwave background radiation, the oldest light in the universe, is almost perfectly uniform in every direction. It has the same temperature to within 1 part in 100,000, no matter which way you look. This is powerful evidence that the universe truly is isotropic on the largest scales. there is no special direction. But here is where it gets interesting. In 2005, a group of researchers analysing the cosmic microwave background data from the UMAP satellite noticed something strange. They found that the large-scale patterns in the CMB, specifically the lowest multipole moments, seemed to be aligned along a particular axis in the sky. This axis passed roughly through the constellation Virgo and was quickly nicknamed the Axis of Evil by cosmologist Kate Land, because if it were real, it would violate the cosmological principle. It would mean the universe has a preferred direction. The debate about the Axis of Evil has continued for 2 decades. Subsequent observations from the Planck satellite, which mapped the CMB with much higher precision, found that the alignment is still there. It has not gone away. But most cosmologists believe it is either a statistical fluke, an artifact of how we subtract foreground emissions from our galaxy, or some subtle systematic error in the data processing. If it were real, if the universe truly had a preferred direction, it would require completely new physics. It would mean the cosmological principle is wrong. It would mean the universe is fundamentally asymmetric. As of the latest analyses, the consensus is that the universe probably is isotropic, and the apparent alignment is not physically real. But the case is not completely closed. It remains one of the most tantalizing anomalies in cosmology. The universe might have a preferred direction. We do not know for certain that it does not, and that uncertainty itself is fascinating. There is another observation that has stirred controversy. In 2008, a team of researchers led by Alexander Kashlinsky at NASA's Goddard Space Flight Center reported evidence of what they called dark flow. They found that large clusters of galaxies over a huge patch of the sky seemed to be moving in the same direction toward a particular point in the sky at velocities that could not be explained by the gravitational pull of any matter we can see in the observable universe. If real, this dark flow would suggest that something beyond the edge of our observable universe, something we can never see, is pulling matter in a specific direction. This would imply a large-scale asymmetry, a preferred direction on the grandest possible scale. However, subsequent studies, including analyses of Planck satellite data published in 2013, found no statistically significant evidence for dark flow. The original detection may have been a systematic error or a result of how the data was filtered. Most cosmologists today consider dark flow unlikely to be real. But again, the question remains open. The universe's large-scale isotropy is an assumption of our standard cosmological model, and every assumption should be tested against observation. Now let us think about the large-scale structure of the universe itself. When we map the positions of galaxies on the largest scales, we find that they are arranged in a vast cosmic web. There are filaments of galaxies stretching across hundreds of millions of light-years, sheets of galaxies forming walls, and enormous empty voids between them. This structure is complex and intricate, but does it have a direction? Does it have an up? The answer, based on our best observations, is no. The cosmic web is statistically isotropic. While any particular local region might have filaments running in some direction, when you average over large enough volumes, the filaments run in all directions equally. There is no preferred orientation to the cosmic web. It is like a random foam, with no top and no bottom. If you rotated the entire cosmic web by any angle, it would look statistically the same. It has no direction. But here is something mind-bending to think about. The cosmic web looks like a 3-dimensional foam or sponge with filaments and voids. But what is the actual topology of the universe? Is it finite or infinite? Is it flat, or does it curve back on itself? Could it be a torus, where if you travel far enough in one direction, you come back to where you started? Could it be even stranger? If the universe is a torus, then travelling in what you think of as one direction would eventually bring you back to your starting point. But here is the bizarre part. On a torus, you cannot consistently define a global direction. On a regular torus, you can still define local directions and transport them around consistently, but on more exotic topologies, like a Klein bottle, you cannot. On a Klein bottle, if you travel around the space and return to your starting point, your sense of left and right has been reversed. A left-handed glove becomes a right-handed glove simply by travelling through the space. Direction itself is inconsistent on such a manifold. We do not know the topology of our universe. Current observations suggest it is flat and likely infinite, but we cannot rule out more exotic topologies on scales larger than our observable universe. It is possible that the universe we live in has a topology where direction itself is globally inconsistent, where there is no way to define a single coherent set of directions for the entire universe. This is not science fiction. This is a genuine open question in cosmology. Now I want to take you somewhere truly deep. We have seen that direction does not exist in the absence of gravity. We have seen that Einstein showed direction is local and path dependent. We have seen that quantum mechanics makes direction indefinite. We have seen that the universe has no preferred direction on large scales. But now I want to ask the deepest question of all. Does space itself actually exist? This might sound like a crazy question. Obviously, space exists. You can move through it. You can measure distances. Things have positions in space. But in the quest for quantum gravity, the attempt to unify general relativity with quantum mechanics, many physicists have come to a radical conclusion. Space might not be fundamental. It might be emergent. It might arise from something deeper and more abstract that has no spatial character at all. One of the leading approaches to quantum gravity is called loop quantum gravity. In this theory, space is not smooth and continuous. It is made up of discrete chunks, tiny nodes connected by links, forming a structure called a spin network. The geometry of space, distances, areas, volumes, all emerge from the mathematical properties of this network. But the network itself does not exist in space. It is space. Or rather, space is what the network looks like on large scales. In a spin network, the concept of direction is not built in. The network has nodes and links and quantum numbers associated with them. Direction only emerges when you zoom out far enough that the network starts to look like smooth, continuous space. At the most fundamental level, in this theory, there are no directions. There is just an abstract mathematical structure from which the illusion of smooth, directed space emerges at large scales. Another approach to quantum gravity comes from string theory, specifically from something called the holographic principle and the ADS-CF correspondence. In this framework, originally discovered by Juan Maldacena in 1997, a gravitational theory in a volume of spacetime is completely equivalent to a quantum theory on the boundary of that spacetime. All the information about what happens in the bulk, including all its spatial directions, is encoded on a lower dimensional boundary that has fewer spatial directions. What this means is staggering. It suggests that one of the spatial directions in our universe might be entirely emergent. It might not fundamentally exist. It might arise from entanglement patterns in a lower dimensional quantum system. Mark van Raamsdonk at the University of British Columbia showed in 2010 that quantum entanglement might be the glue that holds spacetime together. If you remove the entanglement between two regions of a quantum system, the corresponding regions of spacetime pull apart and disconnect. Spatial connectivity, the very fabric that allows directions to exist, might be created by quantum entanglement. In 2013, Juan Maldacena and Leonard Susskind proposed what they called ER equals EPRAR, suggesting that quantum entanglement. The connection between two particles that Einstein called spooky action at a distance is actually the same thing as a wormhole, a bridge in spacetime connecting two points. If this is correct, then the very existence of space and its directions is a consequence of quantum entanglement between fundamental degrees of freedom. Let me put this all together. At the most fundamental level, according to our best current theories of quantum gravity, space does not exist. What exists is some kind of abstract quantum information. From the patterns of entanglement in this quantum information, something emerges that we experience as space, as distance, as direction. Up and down are not just absent in the raw universe. They are multiple levels of emergence away from fundamental reality. First, quantum information gives rise to space-time through entanglement. Then, the curvature of that emergent space-time creates local notions of direction through gravity. Then, biological organisms with vestibular systems interpret those local directions as absolute up and down. At every level, direction becomes less and less fundamental, more and more constructed, more and more illusory. You are sitting there, feeling confidently oriented in space, feeling gravity pull you down, feeling certain about which way is up. But that certainty is built on an illusion, on an illusion, on an illusion. At the quantum information level, direction does not exist. At the space-time level, direction is local, relative, and path-dependent. At the brain level, direction is a constructed interpretation that your brain can get wrong and that collapses entirely in the absence of gravity. At no level is up fundamentally real. Now let us talk about what this means for the future of humanity. Because this is not just abstract physics, this has enormous practical consequences for our species' future in space. When engineers design spacecraft and space stations, they face a fundamental problem. Humans need direction. Our bodies evolved with a constant gravitational reference. Without it, we get sick, we get confused, our muscles atrophy, our bones dissolve. We are creatures of direction, and space has none to offer us. The International Space Station has an interesting solution to this problem. Even though there is no actual up in orbit, the ISS has a designated up and down. The modules are oriented so that labels and equipment faces have a consistent orientation. The ceiling is always the ceiling. The floor is always the floor. Even the lighting is designed to come from above, reinforcing the visual illusion of direction. NASA learned from early space stations that without these visual cues, astronauts become more disoriented and less productive. The human brain needs the fiction of direction to function well, even when direction does not physically exist. But this is just a psychological trick. It does not solve the physical problems that come from the absence of gravity. Without gravitational loading, muscles lose up to 20% of their mass within the first 2 weeks in space. Bones lose about 1 to 2% of their density per month. The heart reshapes itself, becoming more spherical because it no longer has to pump blood against gravity's pull in a specific direction. Blood redistributes toward the head, causing facial puffiness and potentially increasing intracranial pressure. Eyes change shape, and many astronauts return from space with worse vision than when they left, a condition now called spaceflight-associated neuroocular syndrome. All of these problems stem from the same root cause. Our bodies were built to exist in a directional gravitational field. Up and down are not just psychological conveniences, they are physiological necessities, built into the structure of our bones, the pumping of our hearts, the pressure regulation of our eyes. Without direction, our bodies slowly fall apart. The solution that most space engineers envision for long-duration spaceflight is artificial gravity through rotation. If you spin a spacecraft or a space station, the centrifugal effect pushes everything toward the outside of the rotation. This creates a simulated gravity, an artificial down that points outward from the axis of rotation. People living inside a rotating habitat would feel their feet pulled toward the outer wall, and they could walk normally, and their bodies would experience the directional loading they need. The idea is not new. Wernher von Braun proposed rotating space stations in the 1950s. Arthur C. Clarke featured them in his novels. The movie 2001: A Space Odyssey famously depicted a rotating station. But actually building one presents enormous engineering challenges. The structure must be large enough that the rotation rate is low, otherwise the Coriolis effect creates disorienting forces on the body. If the rotation is too fast, Moving your head feels wrong because the rotation adds to or subtracts from the vestibular signal. Studies suggest that the rotation rate should be no more than about 2 revolutions per minute to avoid motion sickness, which means the radius of the station needs to be at least 200 meters to generate Earth-like artificial gravity. Gerard O'Neill, a physicist at Princeton, proposed enormous rotating habitats in the 1970s. His O'Neill cylinders would be kilometers across, large enough to have landscapes, weather, and small cities inside them. In an O'Neill cylinder, you would look up and see the other side of the cylinder above you, with land and lakes and clouds hanging overhead. Down would point outward toward the wall of the cylinder. Up would point toward the central axis, where you would be weightless. A completely artificial direction, created by rotation, providing the physiological loading that human bodies require. But think about how strange this would be. In an O'Neill cylinder, if you climbed a tall enough ladder, you would become progressively lighter as you moved toward the axis. At the axis itself, you would be weightless again, and there would be no direction at all. You would be in the same situation as the astronauts. Up and down would fade away as you climbed. Direction would literally thin out and disappear as you moved through space within the same habitat. A child growing up in such a habitat would understand viscerally that direction is created by rotation and diminishes with distance from the wall. They would know in their bones that up is not real, that it is manufactured. Mars presents a different challenge. Mars has gravity, but only 38% of Earth's. 38% of Earth's gravity is enough to give you a down, enough to keep your otolith crystals pulled in a direction, enough to make objects fall. But is it enough to keep your body healthy? We do not know. We have extensive data on zero gravity from the ISS and on full gravity from Earth, but we have almost no data on partial gravity. We do not know if 38% is enough to prevent bone loss, muscle loss, and eye problems. It might be. It might not. This is one of the biggest unknowns in planning for Mars colonization. And then there is the psychological dimension. What happens to the human psyche when direction becomes obviously artificial or partial? On Earth, we take direction for granted. It feels fundamental. It feels absolute. But a Mars colonist would know that their down is weaker than Earth's down. A resident of a rotating habitat would know that their down is created by spinning and would disappear if the rotation stopped. An astronaut on a long interstellar journey might spend years in zero gravity with no direction at all, and then arrive at a destination with a completely different gravitational field and have to orient themselves to a new down. How would this affect human psychology over generations? Would people who grew up without a fixed gravitational direction have a different relationship with certainty? Would they be less prone to absolute thinking? Would they understand instinctively that perspective is relative, that the frame of reference determines what you see, that there is no universal truth about orientation? It is a fascinating speculation. There is a researcher named Jay Buckey at Dartmouth's Geisel School of Medicine who has been studying the psychological effects of isolation and spatial disorientation in spaceflight analogues. His work suggests that long-duration directionlessness does not just cause physical symptoms, it causes a subtle existential unease. The brain's spatial processing systems are deeply connected to memory, to sense of self, to emotional regulation. The hippocampus, which is crucial for forming new memories and navigating space, relies on directional cells, grid cells, and place cells that all assume a gravitational reference. What happens to memory and identity when these systems lose their reference signal? Preliminary evidence suggests that spatial memory is impaired in microgravity, and this might have cascading effects on other forms of memory and cognitive function. Now let me take you to an even deeper level. We have been talking about direction as a physical phenomenon, as a neurological construction, as an engineering challenge. But let us now think about it philosophically. What does the non-existence of absolute direction tell us about the nature of reality itself and our relationship to it? The philosopher Immanuel Kant, writing in the 1780s, argued that space was what he called a form of intuition. He did not believe space was a property of the world outside our minds. He believed it was a framework that our minds impose on experience in order to make sense of it. For Kant, space with its directions was something contributed by the perceiving mind, not something discovered in the external world. For 2 centuries, most scientists dismissed Kant's view as philosophical speculation. Space was obviously out there, obviously real, obviously independent of our minds. But look at what modern physics tells us. Space might not be fundamental. It might emerge from quantum information. Direction does not exist at the quantum level. It is created by the curvature of emergent spacetime. And even then, it only becomes the crisp, absolute direction you experience, because your brain constructs it from ambiguous sensory signals. At every level, direction is more like something added by the process of observation and cognition than something found in raw reality. This is not the same as Kant's view. Modern physics does not say space is purely mental. It says space is emergent, which is different. But the parallel is striking. Both Kant and modern physics agree that the directed space you experience is not a raw feature of ultimate reality. It is a construction, built somewhere between the abstract quantum substrate and your conscious experience. And this raises the most dizzying question of all. If direction is constructed, what else is? We already know that colour is a construction. There are no colours in the external world. There are only electromagnetic wavelengths, and your brain assigns colours to them. We know that sound is a construction. There are only pressure waves in air, and your brain interprets them as tones and timbres. We know that solidity is a construction. Atoms are mostly empty space, and what you experience as solid matter is just electromagnetic repulsion between electron clouds. And now we know that direction is a construction. There is no up or down in the universe. Your brain makes it up based on gravity and vision. So what is left? What features of your experience are actually out there in the world, unconstructed, uninterpreted, raw, some physicists would say, mathematical structure? The equations, the symmetries, the relationships between quantities, these might be fundamental, but they do not look anything like the world you experience. They are abstract patterns, not concrete objects with positions and directions and colours and sounds. The world you experience, the vivid, rich, directed world of your daily life, with its clear up and down, its solid objects, its colours and sounds, might be entirely a construct of your nervous system, built on top of a reality that is unimaginably abstract and alien to human intuition. And the first clue to this, the first crack in the illusion, is the simple fact that up does not exist in space. Let me bring this back to concrete science for a moment, because I do not want to leave you floating in abstraction. Let us talk about what we actually know about how the brain creates the sense of direction, and how this connects to some of the most exciting neuroscience of the last decade. In 2014, the Nobel Prize in Physiology or Medicine was awarded to John O'Keefe, May-Britt Moser, and Edvard Moser for their discovery of the brain's internal GPS system. O'Keefe discovered place cells in the hippocampus in the 1970s, cells that fire when you are in a specific location. The Mosers discovered grid cells in the entorhinal cortex, cells that fire in a regular hexagonal pattern as you move through space, creating an internal coordinate system. They also found head direction cells which fire when you face a particular direction, acting like an internal compass. These cells create your brain's internal map of space. They tell you where you are, which way you are facing, and how far you have travelled. And crucially, they are all anchored to the gravitational direction. The head direction cells define directions relative to the horizontal plane, which is defined by gravity. The grid cells create their hexagonal pattern on the floor, which is perpendicular to gravity. the entire system assumes a gravitational reference. So what happens to these cells in space? Research published by Yuri Bubnikova and colleagues studying rats in simulated microgravity showed that head direction cells become unstable. They lose their preferred firing directions. Grid cells become disorganized. Place cells still function but become less specific. The brain's entire spatial navigation system degrades without gravity. For astronauts, this manifests as difficulty forming spatial memories. They report that it is harder to remember where things are on the space station. They sometimes get lost in modules they have been living in for months. Their internal map of the station is less reliable than their internal map of their home on Earth. And this makes sense. The navigation system that builds internal maps requires a gravitational reference to function properly. Without it, the maps are fuzzier, less reliable, harder to form and maintain. This has implications that go far beyond navigation. The hippocampus, where place cells live, is also central to episodic memory, the ability to remember events in your life. Episodic memories are strongly spatial. When you remember a birthday party, you remember where it happened, where people were standing, which direction you were facing. If the brain's spatial system degrades in microgravity, it might impair the formation of new episodic memories. Astronauts on very long missions might find that their memories of the mission are vaguer, less detailed, less spatially grounded than their memories of life on Earth. And there is an even more speculative possibility. Some neuroscientists, particularly those working in the framework of predictive processing, believe that the brain's spatial system is not just for navigation. They believe it provides a general purpose framework for organizing all kinds of information. The concept of near and far, the concept of direction, the concept of being in a particular place in a cognitive space of ideas, all of these might piggyback on the neural machinery originally evolved for physical navigation. If this is correct, then the loss of gravitational direction might subtly affect not just physical navigation, but cognition itself. The way you think, the way you organize ideas, the way you reason about abstract concepts, might all be subtly shaped by the fact that you live in a world with a clear up and down. This is speculative, but it raises a fascinating question about human evolution in space. If future humans grow up in environments without consistent gravity, without the same clear directional reference, will they think differently? Not just about space and direction, but about everything. Will their cognitive architecture be subtly different from ours? Will they organize ideas differently, remember things differently, reason differently? Will they be, in some cognitive sense, a different kind of mind? Let us go back to physics now. I want to explore one more dimension of this topic that I think is the most mind-bending of all. We have talked about direction in space. But what about direction in time? Too, in physics, time is often treated as a direction. We move forward in time. The past is behind us. The future is ahead. Time has an arrow, a preferred direction, from past to future. But just as spatial direction turns out to be illusory or emergent, the direction of time might be equally constructed. The fundamental laws of physics, with one tiny exception related to the weak force, are time-symmetric. They work the same way forward and backward in time. If you film any fundamental physical process and play the film backward, it looks like a perfectly valid physical process. A billiard ball collision looks the same forward and backward. An orbit looks the same forward and backward. Even quantum mechanical processes, at their most fundamental level, are time-symmetric. So why does time seem to have a direction? Why does the future seem different from the past? The standard physics answer is entropy. The second law of thermodynamics says entropy always increases, disorder always grows, things fall apart, they do not come together spontaneously, and this gives time a direction. But this is a statistical fact, not a fundamental law. Entropy increases because there are vastly more disordered states than ordered states, so a system is overwhelmingly likely to evolve toward disorder. But it does not have to. There is no fundamental law that forbids entropy from decreasing. It is just incredibly unlikely. So the direction of time, the arrow pointing from past to future, might be just as constructed, just as non-fundamental as the direction of up. Both are emergent from deeper physics. Both feel absolute and undeniable in our experience. And both might be illusions of perspective. In 2004, physicists Sean Carroll and Jennifer Chen proposed that the arrow of time might be a local phenomenon, just like spatial direction. In the much larger multiverse, time might not have a preferred direction. Different regions might have opposite arrows of time. What we experience as the inexorable flow from past to future might be just our local perspective on a much larger structure that has no preferred temporal direction. Just as what we experience as up is just our local perspective on a space-time that has no preferred spatial direction. Do you see the pattern? At every level, in every domain of physics, the same lesson repeats. Direction, whether spatial or temporal, is not fundamental. It is emergent. It is local. It is perspective dependent. It is constructed. The universe at its most fundamental level might have no directions at all, neither in space nor in time. It might be an abstract structure of relationships and symmetries, from which the directed world of our experience somehow emerges. Let me now tell you about one of the most beautiful thought experiments in all of physics. It is called the bucket argument, and it was originally proposed by Newton himself in 1687. But its resolution 200 years later by Ernst Mach, and then 300 years later by general relativity, tells us something profound about the nature of direction and rotation. Newton imagined a bucket of water hanging from a rope. You twist the rope and let it go. The bucket starts spinning. At first the water stays still and the bucket spins around it. Then gradually the water starts spinning too, and its surface becomes concave, higher at the edges, lower at the centre. The water curves up at the sides because the spinning creates centrifugal effects. Newton asked, what is the water spinning relative to? At first you might say it is spinning relative to the bucket. But at the end, when the water and the bucket are spinning together at the same rate, the water is still curved, still showing the effects of rotation. It is no longer spinning relative to the bucket. So what is it spinning relative to? Newton said it must be spinning relative to absolute space itself. The rotation is absolute, not relative. And this means directions, defined by the rotation axis, are absolute too. This argument stood unchallenged for 200 years. Then Ernst Mach proposed a radical alternative. Mach said the water is not spinning relative to absolute space. It is spinning relative to all the distant matter in the universe, all the distant stars and galaxies. If you could somehow remove all the distant matter and spin the bucket in otherwise empty space, Mach claimed, the water would not curve. The effects of rotation, and thus direction, come from the relationship between local matter and distant matter, not from some absolute background space. Einstein was deeply influenced by Mach's idea, which became known as Mach's principle. When Einstein developed general relativity, he hoped it would embody Mach's principle fully. The result was complicated. General relativity partially incorporates Mach's ideas, but not completely. In general relativity, the geometry of spacetime is determined by the distribution of matter and energy everywhere. So the distant matter does influence local directions and rotation through its effect on spacetime curvature. But general relativity also allows solutions, like rotating universes, where the role of distant matter is unclear. The debate about Mach's principle continues to this day. But the key point for us is this. Even the concept of rotation, which seems to define a direction, might not be absolute. It might be relational, defined only by the relationship between the rotating thing and the rest of the matter in the universe. Strip away the distant galaxies, and maybe rotation itself becomes meaningless. Maybe the axis of rotation, which defines a direction in space, only exists because there is distant matter to define it against. This is another way in which direction might be emergent, not from quantum information this time, but from the relational structure of the universe. Direction might exist only because there are multiple things in the universe to define directions between. In a universe with only one object, there might be no directions at all. You need relationship, you need multiplicity, you need structure for direction to emerge. Now let me draw all of these threads together and show you the big picture. Because we have explored this topic from so many angles, and I want you to see how they all connect. Start at the bottom, at the most fundamental level. Quantum gravity theories suggest space itself is emergent. It arises from abstract quantum information, from entanglement patterns, from spin networks or holographic codes. At this level, there are no directions. There are only mathematical relationships. Rise one level. Space emerges with its geometry and curvature. General relativity describes this level. Here, directions exist, but they are local, relative to local curvature, path-dependent, and frame-dependent. There is no absolute up. There is only the local behavior of geodesics in curved spacetime. Rise another level. Large-scale structure forms in the universe. Galaxies, clusters, the cosmic web. On the largest scales, there is no preferred direction. Isotropy rules. The universe looks the same in every direction. Statistically, rise another level. Planets form. Their mass curves spacetime around them. Now locally there is a clear direction toward the center of the planet. We call this direction down, but it is purely local, purely created by the planet's mass, purely a feature of this particular region of curved spacetime. Rise another level. Biological organisms evolve on the planet's surface. They develop vestibular systems, gravity-sensing organs that detect the direction of local spacetime curvature. Their brains interpret this signal as absolute down and construct a sense of absolute up. They feel certain about direction. They cannot imagine it not existing. Rise one final level. Those organisms develop technology. They leave the planet. They enter microgravity. And suddenly, the entire construction collapses. Their vestibular systems go silent. Their brains malfunction. They discover, viscerally and undeniably, that direction was never real. It was a local phenomenon, a biological construction built on a gravitational signal that only exists near massive objects in a universe that is mostly empty space with no direction at all. That is the complete picture. From quantum gravity to human neuroscience, direction is constructed at every level. It is not a feature of ultimate reality. It is a feature of particular local conditions, interpreted by particular evolved nervous systems, experienced as absolute truth by conscious minds that have never known anything else. And I find this beautiful. Not terrifying. Beautiful, because it tells us something profound about the relationship between reality and experience. It tells us that experience is not a transparent window onto reality. It is a creative construction built by our brains for survival purposes, taking the raw abstract structure of the universe and rendering it in a form we can navigate and use. Up is not a lie exactly, it is a tool. A useful fiction, a simplification that allows us to function in our local environment. But it is not the truth about the universe. The truth is deeper, stranger, more abstract, and more beautiful than any simple direction. Let me now discuss something that connects directly to the future of physics. The problem of quantum gravity, the attempt to unify general relativity and quantum mechanics, is often described as the biggest unsolved problem in physics. And one of the central challenges of quantum gravity is precisely the problem of direction and space. In general relativity, space-time is a smooth manifold with a well-defined geometry. You can talk about directions, curves, geodesics. In quantum mechanics, things are discrete, probabilistic, uncertain. When you try to combine the two, you run into a fundamental conflict. If space is supposed to be smooth and continuous, as general relativity assumes, but quantum mechanics makes everything discrete and uncertain at small scales, then what happens to the geometry of space at the Planck scale? At distances of about 10 to the negative 35 meters. Most quantum gravity researchers believe that at the Planck scale. The smooth geometry of space breaks down completely. Space becomes foamy, uncertain, fluctuating. The concept of direction at this scale becomes meaningless because the geometry itself is not well defined. You cannot define a direction in a space whose geometry is in quantum superposition, fluctuating between different configurations. This is called space-time foam, a concept proposed by John Wheeler in 1955. At the smallest scales, space is not smooth, it is turbulent, chaotic, uncertain, directions fluctuate, distances fluctuate. The very dimensionality of space might fluctuate. You might have 4 dimensions in one fluctuation and 7 in another. The smooth, directed space we experience is an average, a coarse-grained approximation of this underlying quantum chaos. And the challenge of quantum gravity is to explain how the smooth, directed space of our experience emerges from this underlying quantum foam. How does direction arise from directionlessness? How does geometry emerge from geometric chaos? This is one of the deepest questions in all of physics, and we do not yet have a complete answer. Loop quantum gravity offers one approach. In loop quantum gravity, space is made of discrete quanta of volume and area. These quanta are organized in a network, and the smooth geometry of space emerges from the collective behavior of many such quanta. Just as the smooth behavior of water emerges from the collective behavior of many water molecules. Direction in this picture is like the flow direction of water. It is a macroscopic, emergent property that does not exist at the level of individual atoms. String theory offers another approach. In string theory, the fundamental objects are one-dimensional strings vibrating in a 10 or 11-dimensional spacetime. The 6 or 7 extra dimensions are compactified, curled up so small we cannot see them. In this picture, the directions of the extra dimensions are hidden, rolled up. We only see 3 spatial directions because the others are too small to detect. But they might still influence physics at high energies, and the process by which some dimensions become large and directional while others remain small and hidden is still not fully understood. There is also a more radical approach called causal set theory. In this framework, spacetime is not continuous at all. It is a discrete set of events connected by causal relations, meaning which events can influence which other events. That is all there is, just events and causal connections. Space, time, directions, geometry, all of these emerge from the pattern of causal connections. At the fundamental level, there is no space, no direction. There are only events happening in a causal order. In causal set theory, asking which way is up is literally a meaningless question at the fundamental level. The fundamental level has no up, no space, no geometry. It only has the causal structure of events. Direction is something that emerges at large scales when enough events are connected in the right patterns to create something that looks like smooth spacetime. I find it remarkable that so many different approaches to quantum gravity, developed independently by different groups of physicists with different mathematical tools and different philosophical assumptions, all converge on the same conclusion. Space and direction are emergent. They are not fundamental. The universe at its deepest level is not spatial. It is something else, something more abstract, from which spatiality emerges. Now let me take a slight detour to discuss something related that I think will fascinate you. The relationship between direction and consciousness. We have established that direction is constructed by the brain. But the brain is part of the physical universe. It is made of atoms, which follow quantum mechanics, which exists in space-time, which is described by general relativity. So we have a strange loop. The brain is part of physical reality. Physical reality has no inherent direction, but the brain constructs direction as part of experience. And experience is how we access physical reality. This circular relationship between observer and reality is at the heart of many interpretations of quantum mechanics. In the Copenhagen interpretation, the act of observation plays a special role in causing quantum systems to take on definite values. Without observation, properties are indefinite. With observation, they become definite. Direction, as we discussed, is among the properties that are indefinite in quantum mechanics until observed. So there is a sense in which direction only fully exists when conscious observers construct it. Not in the mystical New Age sense that consciousness creates reality, but in the physical sense that direction as a definite, experienced property requires both a physical system, space-time curvature, and an observer system, a brain with a vestibular system, to fully manifest. Neither one alone produces direction. You need both. You need the universe to provide the curvature, and you need a nervous system to interpret that curvature as direction. This is a theme that keeps appearing in modern physics. Properties we thought were absolute and observer-independent turn out to be relational, existing only in the relationship between systems. Direction is relational. Simultaneity is relational, as Einstein showed with special relativity. Even the number of particles in a quantum field is relational, as the Unruh effect demonstrates. An accelerating observer sees particles where an inertial observer sees empty space. Reality seems to be fundamentally relational, not absolute. And direction is perhaps the simplest, most intuitive example of this relationality. It feels absolute. It feels like an obvious, undeniable feature of the external world. But it is not. It is a relationship between your body and the curved space-time around it, interpreted by your brain into an experience of absolute orientation. Change the relationship, change the experience. Move to space, and direction vanishes. Move to a different gravitational field, and direction changes. You never access direction in itself. You only access your brain's interpretation of your body's relationship with local space-time curvature. Let me now discuss something practical and specific. How does the absence of up and down affect the design of everything humans build for space? When you design a building on Earth, direction is fundamental to the design. Floors are horizontal, walls are vertical, windows are on the sides, the roof is on top, water flows down, hot air rises. Everything is oriented by gravity. But when you design a habitat for space, none of these assumptions hold. On the International Space Station, every surface can be a floor. Astronauts work on what would be the ceiling of a room on Earth. They sleep attached to walls. Equipment is mounted on all 6 surfaces of a module. This creates a fundamentally different relationship with architectural space. There is no up or down to a room. There is only inside and outside, center and periphery. Early space stations did not account for this very well. On the Soviet Salyut stations in the 1970s, modules were designed in a more or less conventional Earth-like orientation, with equipment primarily on what was designated as the floor and walls. But astronauts quickly discovered that this was wasteful. Why leave the ceiling empty when you could mount equipment there? In microgravity, the ceiling is just as usable as the floor. When the Soviets designed their later stations, particularly Mir, they began to use all surfaces more equally. But they kept consistent color coding. The ceiling was always white. The floor was always dark. The walls were intermediate colors. This gave astronauts a visual reference for orientation, even though there was no physical basis for it. Psychologists found that this color coding significantly reduced disorientation incidents. The International Space Station took this further. Each module has consistent orientation markings. Labels are always readable from one particular orientation, which defines the local up for that module. Handholds and foot restraints are positioned assuming you approach from a particular orientation. The entire station, despite floating in zero gravity, maintains a consistent fiction of direction through design choices. But future space habitats might take very different approaches. There have been proposals for space habitats that are designed without any preferred orientation at all. Spherical modules where every surface is a working surface. Habitats designed for truly three-dimensional living, where the concept of up and down is not just absent physically, but deliberately abandoned psychologically as well. Some architects have proposed that this would be liberating, allowing much more efficient use of volume and enabling types of movement and interaction that are impossible in gravity. The human factors research on this is still in its early stages. We do not know whether humans can be fully healthy and productive in a truly directionless environment for long periods. The evidence from the ISS suggests that humans prefer and function better with at least a visual fiction of direction. But astronauts also report that after a few months, they become very comfortable with the three-dimensional nature of microgravity and can navigate confidently in any orientation. Perhaps with enough time, humans can fully adapt to directionlessness. This matters for the future of space exploration. If we send humans to Mars on a 6-month journey, should the ship have artificial gravity through rotation, or should we accept microgravity and help the crew adapt? If we build a permanent base on the Moon, where gravity is only 1/6 of Earth's, will the brain's vestibular system work properly with such a weak signal? Will 1/6 gravity be enough to keep the navigation cells in the hippocampus properly calibrated? These are open questions, and they all come back to the fundamental fact that up does not exist in space, and the human brain was not designed for a universe without direction. Let me now take you on one more journey through physics. I want to talk about symmetry, because symmetry is the deepest concept in modern physics, and direction, or the absence of direction, is intimately connected to it. In physics, a symmetry is a transformation you can perform on a system that leaves its behaviour unchanged. If you rotate a system and it behaves the same way, that is rotational symmetry. If you move it to a different location and it behaves the same way, that is translational symmetry. If you do the experiment today or tomorrow and get the same result, that is time translation symmetry. Emmy Noether proved in 1918 that every symmetry corresponds to a conservation law. Rotational symmetry corresponds to conservation of angular momentum. Translational symmetry corresponds to conservation of linear momentum. Time translation symmetry corresponds to conservation of energy. Now, when we say the universe has no preferred direction, what we are really saying in physics language is that the laws of physics have rotational symmetry. They look the same regardless of which way you orient your experiment. You can point your lab east, west, north, south, and you will get the same results. No direction is special. This rotational symmetry, through Noether's theorem, gives us conservation of angular momentum. And conservation of angular momentum is one of the most important laws in physics. It explains why planets orbit in ellipses, why galaxies spin, why figure skaters spin faster when they pull in their arms, why gyroscopes work. All of this comes from the simple fact that the universe has no preferred direction. But notice the beautiful circularity here. The universe has no up because the laws of physics are rotationally symmetric. And because the laws are rotationally symmetric, angular momentum is conserved. And conservation of angular momentum creates spinning objects, like planets. And spinning planets create gravitational fields. And gravitational fields create a local down. And your brain interprets that local down as absolute direction. So direction, which does not exist at the fundamental level because of rotational symmetry, emerges at the local level precisely because of a consequence of that same rotational symmetry. The universe's symmetry, its lack of preferred direction, leads through a chain of physical consequences to the creation of local directions near massive spinning objects. The absence of universal direction creates local direction. It is self-referential. It is beautiful. Let me go even deeper into symmetry. We discussed CPEAT symmetry earlier, but there is an even more fundamental symmetry principle in modern physics called gauge symmetry, and it has a profound connection to our topic. In quantum electrodynamics, the theory of electromagnetic interactions, there is a symmetry called U-gauge symmetry. This means that you can rotate the phase of a quantum field by a different amount at every point in space, and the physics does not change as long as you also adjust the electromagnetic field to compensate. This is called a local gauge symmetry because the transformation is different at every point. In a deep mathematical sense, gauge symmetries are about the freedom to choose reference frames at each point independently. They are about the fact that there is no absolute standard of comparison between different points in space. You cannot compare the phase of a field here with the phase of a field there without introducing a connection, a rule for how to parallel transport the comparison between the 2 points. This is exactly the same mathematical structure we encountered earlier when we discussed how directions cannot be compared between different points in curved spacetime. In general relativity, you cannot compare directions at different points without a connection. In gauge theory, you cannot compare field phases at different points without a connection. The mathematical parallel is not a coincidence. It reflects a deep truth about physics. The truth is this: at the most fundamental level, there are no absolute quantities at any point. Everything is relative. Everything is defined only in relationship to other things through connections that link different points. Direction is relative. Phase is relative. Even the distinction between different forces is relative in some contexts. Grand unified theories suggest that the strong force, weak force, and electromagnetic force are all aspects of a single force, distinguishable only because of how symmetry is broken in our low-energy world. The universe is built on symmetry and relativity and the absence of absolute reference. Direction is just one example of this deeper principle. Nothing has an absolute value. Everything is defined relationally. And what we experience as the directed, definite, concrete world is a world of broken symmetries and emergent relationships, not a world of fundamental absolutes. This brings me to the concept of symmetry breaking, because while the fundamental laws are rotationally symmetric, the actual state of the universe is not. The universe is full of massive objects, each creating their own local sense of direction. Galaxies have planes of rotation. Stars have poles. Planets have gravitational fields pointing toward their centers. These are all examples of spontaneous symmetry breaking, where a system whose laws have a symmetry nevertheless ends up in a state that does not exhibit that symmetry. Think of a ball balanced on top of a hill. The hill is symmetric, the same in every direction. But the ball must eventually fall, and it will fall in some particular direction. The direction it falls breaks the symmetry. It is not determined by the laws themselves, but by tiny random fluctuations. Once it falls, there is a preferred direction down the hill. But this direction is accidental, contingent, not fundamental. The same is true of the directions we experience. The Earth orbits in a particular plane. This plane defines particular directions for us. Up is perpendicular to the orbit, roughly. But this plane is an accident of the particular angular momentum of the dust cloud that formed the solar system. A different set of initial conditions would have given us a different orbital plane, a different up. Our direction is contingent, historical, accidental, not fundamental. And on the cosmic scale, the same applies. The cosmic web has filaments running in various directions, but these directions are set by the random quantum fluctuations in the early universe that seeded the growth of structure. Had those fluctuations been slightly different, every filament, every galaxy, every star would point in a different direction. The specific directions of everything in the universe are historical accidents, traces of primordial randomness. They are not built into the laws of physics. The laws say, no direction is preferred. Reality says, but this particular direction happened to emerge here. and that particular direction happened to emerge there. The conflict between the symmetric laws and the asymmetric reality is resolved by recognizing that the specific state of the universe is one of many possible states, all equally allowed by the laws, with no particular direction favored by the fundamental physics. Now let me tell you about something that I find particularly mind-bending. We have been assuming that the universe has 3 spatial dimensions, 3 directions you can independently move in: left, right, forward, backward, up, down. But why 3? This is one of the deepest unsolved problems in physics. Why does our universe have exactly 3 large spatial dimensions? String theory requires 10 or 11 dimensions, with the extras compactified. But why did exactly 3 dimensions grow large? Some physicists have proposed anthropic arguments. Only universes with 3 large spatial dimensions allow stable planetary orbits and stable atoms, both of which are necessary for life. In 2 dimensions, planets cannot orbit stably. In 4 or more spatial dimensions, the inverse square law of gravity becomes an inverse cube or higher power law, and orbits are unstable. But others find these arguments unsatisfying. They want a dynamical explanation. They want to understand what physical mechanism caused 3 dimensions to expand while the others stayed small. This remains an open question. But here is what I find fascinating about this for our topic. The very concept of direction, the very concept of up and down, depends on the dimensionality of space. In 2 spatial dimensions, there would be no up. Everything would be flat, like a plane. There would be left, right, and forward, backward, but no up, down at all. In 4 spatial dimensions, there would be a new direction that we cannot even conceive of, a direction perpendicular to all 3 of our directions. We cannot visualize it. We cannot imagine what it would feel like to move in that direction, but mathematically, it is perfectly well defined. So not only does up not exist in the absolute sense we think it does, but the very number of possible directions is a contingent feature of our universe that could have been different. In a different universe, there might be 4 independent directions instead of 3, or 2, or 7. The fact that we have exactly 3 types of direction, that we can go up, down, left, right, and forward, backward, and no other independent way, is not a logical necessity. It is a physical fact about our particular universe that demands explanation. Let me shift now to something visceral and immediate. I have been discussing deep physics and abstract ideas, but let me ground this in the actual lived experience of human beings who have confronted directionlessness. Chris Hadfield, the Canadian astronaut who commanded the International Space Station in 2013, described the experience of arriving in space with remarkable clarity. He wrote about the moment he first floated out of the space shuttle into the station. He was floating in the middle of a module, with no floor beneath his feet, no ceiling above his head, and he described a moment of pure disorientation so profound that he felt like he was falling in every direction simultaneously and in no direction at all. His brain simply had no framework for interpreting his situation. He was not upside down or right side up. He was not falling or rising. He was just floating, and his brain could not categorize this experience. Scott Kelly, who spent 340 consecutive days on the ISS in 2015 and 16, described a different aspect of directionlessness. After months in space, he said, the feeling of being oriented became almost arbitrary. He could be working at a laptop mounted on what was designated as the ceiling, and it felt perfectly normal. Up was wherever his head happened to be pointing. His brain had completely abandoned the vestibular signal and was relying entirely on visual and cognitive cues for orientation. Direction had become a conscious choice rather than a physical sensation. But when Kelly returned to Earth after nearly a year in space, the transition was violent. He described feeling like he was being crushed by gravity. His sense of up was overwhelming after so long without it. His legs swelled, his skin hurt from the pressure of blood being pulled downward. He had rashes and pain from the simple fact of gravity reimposing direction on his body. He described feeling like a newborn, having to relearn how to live in a directed world. Peggy Whitson, who spent 565 days in space over multiple missions, the American record at the time, reported that the transitions between gravity and weightlessness became somewhat easier with experience, but never trivial. Each time she returned to Earth, she spent days feeling unstable, uncertain about direction, having to consciously think about where down was. Her brain had become adept at switching between directed and directionless modes, but the switch was never instantaneous or painless. These are not just interesting anecdotes, they are data points about the relationship between physical reality and human experience. They show us that direction is not a passive perception. It is an active construction that can be disrupted, retrained, and fundamentally altered by changing the physical environment. The brain's model of up and down is plastic, malleable, and ultimately arbitrary. It locks onto whatever signal is available and constructs certainty from that signal, but the certainty is manufactured. Put the brain in a different environment and it will manufacture a different certainty with equal conviction. Now I want to discuss something that might seem tangential at first, but is actually deeply connected: the multiverse. Because if we take seriously the idea that direction is contingent, that the specific directions in our universe are historical accidents of symmetry breaking, then in a multiverse, different universes might have broken their symmetries in completely different ways. In some string theory landscapes, different vacuum states correspond to different configurations of extra dimensions. And the way the extra dimensions are compactified determines what forces exist, what particles exist, and crucially, what the geometry of the large dimensions looks like. It is conceivable that in some regions of the multiverse, space has different properties than in our universe. Maybe different dimensionality, maybe different topology, maybe different relationships between matter and geometry. In such other universes, if they exist, the concept of direction might be entirely different from what we know. A universe with 4 large spatial dimensions would have 4 independent directions instead of 3. Beings in such a universe, if any existed, would have an additional sense of direction that we cannot even imagine. Their version of up would be richer, more complex than ours. Or in a 2-dimensional universe, beings would have a thinner sense of direction. They would know forward and backward, left and right, but up and down would be as unimaginable to them as a 4th spatial direction is to us. This highlights something important. Our sense of direction is not just constructed by our brains, it is constrained by the physics of our universe. We experience 3 types of direction because our universe has 3 large spatial dimensions. Beings in a different universe would experience direction differently because their physics is different. Direction is both neurologically constructed and physically constrained. It lives at the intersection of mind and universe, shaped by both. Let me now talk about gravitational waves and direction. In 2015, the LIGO detectors made the first direct detection of gravitational waves, ripples in spacetime caused by the collision of 2 black holes more than 1 billion light-years away. This detection, announced in February 2016, confirmed a prediction Einstein made a century earlier. But what are gravitational waves in terms of our discussion? They are distortions of direction itself, propagating through space at the speed of light. When a gravitational wave passes through you, the distances between points in space change. In one direction, space stretches. In the perpendicular direction, space compresses. Then they reverse. Stretch, compress, oscillating as the wave passes. The directions of space itself are being rhythmically distorted. This is direction being physically warped and oscillated. The very thing that defines up and down, the geometry of space-time, is vibrating. If a sufficiently powerful gravitational wave passed through you, your sense of direction would be briefly disrupted because the geometry defining direction would be oscillating. You would feel stretched in one direction and compressed in another, and these directions would swap back and forth as the wave passed. In practice, the gravitational waves LIGO detects are incredibly weak. They stretch space by less than 1/10,000th of the diameter of a proton. You cannot feel them. But in principle, near the source of gravitational waves, near colliding black holes or neutron stars, the effect would be enormous. Space would be violently distorted. Directions would oscillate wildly. Up and down would have no stable meaning because the geometry defining them would be in turmoil. This brings us to black holes. And if anywhere in the universe demonstrates that direction is bizarre and non-absolute, it is near and inside a black hole. At the event horizon of a black hole, space-time is curved to such an extreme degree that something remarkable happens. The roles of space and time swap for one of the directions. Inside a black hole, the direction toward the singularity is not really a direction in space at all. It is more like a direction in time. Just as you cannot avoid moving forward in time outside a black hole, you cannot avoid moving toward the singularity inside a black hole. The inward direction has become time-like. You will reach the singularity not because a force is pulling you there, but because that direction has become the future. Reaching the singularity is as inevitable as reaching tomorrow. Think about what this means for direction. Inside a black hole, one of your spatial directions has become temporal. You have lost a spatial direction. Space inside a black hole effectively has one fewer dimension than space outside, in a very real physical sense. The concept of up, meaning the direction away from the singularity, does not exist inside a black hole. Not because there is no gravity, but because that direction has stopped being spatial. You cannot go up inside a black hole for the same reason you cannot go backward in time outside one. It is not a spatial direction anymore. This is perhaps the most dramatic example of how direction can break down in our universe, not just become undefined, as in empty space far from matter, not just become relative, as in different gravitational fields, but actually cease to be a spatial direction at all. It transforms into something else entirely. Space can become time. Direction can become fate. Roger Penrose, who won the Nobel Prize in Physics in 2020 for his work on black holes, proved in 1965 that once a sufficient amount of matter collapses beyond a certain point, the formation of a singularity is mathematically inevitable. This is Penrose's singularity theorem, and it tells us that in our actual universe there exist regions where direction breaks down completely, where the geometry of space becomes singular, where the concept of up and down and left and right simply ceases to be definable. These regions might be hidden behind event horizons, inaccessible to outside observation. But they exist. They are part of our universe. And their existence tells us that direction is not a stable, permanent feature of reality. It can be destroyed. It can be transformed. It can become singular and meaningless. The universe permits the complete annihilation of direction. Now let me bring this discussion to something more immediate and practical. Climate science. You might wonder what climate science has to do with direction, but the connection is more direct than you think. Actually, let me correct myself. I do not want to stray from our topic into areas that are not directly relevant. Let me instead continue exploring the physics of direction with something that connects back to our central theme. Let us talk about the vacuum of space. Empty space. When you look up at the night sky, you see stars scattered across vast distances. Between those stars is what appears to be nothing. Empty space. A void. And in that void there is no up, no down, no direction at all. If you were floating in interstellar space, millions of light years from the nearest galaxy, the gravitational field would be essentially zero. Your otolith crystals would not be pulled in any direction. Your brain would receive no gravitational signal. You would have no sense of direction whatsoever. But here is something remarkable. Even in that apparently empty space, there is something. The quantum vacuum is not truly empty. It seethes with virtual particles popping in and out of existence on timescales too short to observe directly. These virtual particles create what is called the vacuum energy, and this vacuum energy has been measured through the Casimir effect, discovered experimentally by Steve Lamoureux in 1997. Does this quantum vacuum have a direction? The answer is no. The quantum vacuum is perfectly isotropic. It looks exactly the same in every direction. Virtual particles pop into existence in all directions equally. There is no preferred direction in the vacuum. This isotropy of the vacuum is actually one of the foundations of particle physics. If the vacuum had a preferred direction, it would violate Lorentz symmetry, which is one of the most precisely tested symmetries in all of physics. Experiments have tested Lorentz symmetry to extraordinary precision, measuring any possible vacuum anisotropy to be less than 1 part in 10 to the power of 23. The vacuum is symmetric in direction to an almost inconceivable degree of precision. This means that even at the level of the quantum vacuum, the substrate underlying all of particle physics, there is no preferred direction. The universe is directionless at every scale we have been able to probe. From the quantum vacuum to the cosmic microwave background, isotropy holds. Direction simply is not a feature of the universe at any fundamental level. Now I want to discuss an experiment that beautifully illustrates the constructed nature of direction. It involves something called the Vomit Comet, the NASA aircraft that flies parabolic arcs to create brief periods of weightlessness for astronaut training and research. During the parabolic arc, the aircraft is in freefall for about 20 to 30 seconds at a time. During these periods, everything inside the aircraft is weightless, and researchers have used these brief windows of directionlessness to study how quickly the brain responds to the loss of gravitational reference.